Morning, folks. So today, Vector 6, it's the last of the vectors lessons, you might be pleased to hear, or maybe not. Today, we've got to be able to find coordinates of points in the reflection plane, but before we do that, we are going to be able to find the distance between a point and a plane, and then maybe have a look at we will be having a look at a practice exam question. So, perpendicular distance from a point to a plane, in other words, the shortest distance is always the perpendicular distance. So here's your point, here's your plane. We need to find the distance between P and M, and that's a perpendicular distance to it's a perpendicular angle to the plane. This little n thing, should know that, that's also a vector perpendicular to the plane. So given a plane with equation r dot n equals a dot n, and they just called that a dot nd, and a point M outside of the plane, the distance from M to the plane is equal to the distance MP. Makes sense? Where the line MP is perpendicular to the plane, so it meets it at 90 degrees. This means that the direction of MP is, in fact, it's the same as, probably guessed it. Grab my board. N. The vector N. To find this distance MP, we write down a vector equation of the line with direction N through a point M. So we try and find the equation of this line here, which has the same direction as that. Find the intersection P between the line and the plane. So find out where this line hits the plane. And then we can calculate the distance between the 2 points, MP. So the point P is called sometimes called the foot of the perpendicular from point to plane. Just run through this example here. So find the perpendicular distance from the origin to the plane, that thing. So at the top here, we've got the origin, O. We've got this point here, we're going to call this point where it hits the foot of the perpendicular, we're going to call that P, where it hits the plane. And this little thing here is just reminding us that's the 90 degree to the plane vector. So this equation of the plane is, if you want to write it in vector form, the R is X, Y, Z, and it's been dotted with the N, if you remember. Now that must be 1, 2, minus 2, and that equals A dot N, which is 4 here. So what we can see from that is that that's the direction vector we're after. If you wanted it as Cartesian, we might as well write this down and use it later. The Cartesian form of this plane would be x plus 2y minus 2z equals 4. We'll be using that later, but we'll see why in a minute. Right, so our n value is that. So the equation of this line of P to O, or O to P, well, let's do P to O because it have the same n direction. So the equation of that, so equation of P to O can equal a point on the line, which we know is 000, plus some scalar of the direction, which is the same as this one here, 1, 2, minus 2. Lovely. Right, now we need to know, when does this line hit this plane? In other words, what is that coordinate of P there? Well, to do that, we put the line into the plane. So all we have to do is substitute these into that plane here, or into this plane. Looks nicer to substitute into here. So X, so that will be just lambda. Then we've got plus 2 lots of Y, which will be 2 lambda. Then we've got minus 2 lots of Z, which is minus 2 lambda. This all equals 4. So working out here, we've got 1, 5, minus 4. So that's actually, no, it's another 4, isn't it? So we've got 9 lambdas equals 4, and therefore lambda must equal 4 over 9. So we know this line hits the plane when lambda is 4 over 9. So putting 4 over 9 in here, so that's 0 plus 4 over 9, which is 4 over 9. 0 plus 2 4s over 9, which would be 8 over 9. 0 minus 2 lambdas, so that's minus 8 over 9. So that's point P. So now we know point P. We know the origins. What's the distance between those 2 points there? Well, the distance O to P or P to O doesn't really make any difference. It's a bit of Pythagoras, square and square root. So we could do, it's this between, if we're doing O to P or P to O, it really doesn't matter, but 4 over 9 minus 0 squared plus 8 over 9 minus 0 all squared plus minus 8 over 9 minus 0 all squared. If you do that on your calculator, it will come out to, I believe, 4 over 3. Nice number. And that's that one. Super. Okay, we've got another example. This time it's not the origin that we're finding the distance from. We're finding the distance from the point 2, 1, minus 3 to this plane here. So again, we've got sort of a diagram here that maybe it helps explain it. So this is your point 2, 1, minus 3. That we'll call foot of perpendicular, we'll call that P, and this is your perpendicular vector. So if you want to, we call that one M again. So that's M. That's the plane. So off we go. The plane also could be written as R is X, Y, Z. Dot. Got 3, 0, minus 4 equals, obviously, N dot A, whatever that was, it came out as 6. And for later on, when we sub something in to see where the plane meets the line, we need the equation in that form, 3x minus 4z equals 6. So this line, MP, we know it has the same direction as the perpendicular one to the plane because we're after the shortest distance, and that's always perpendicular. So it will be, equation of our line will be R equals, in vector form, point on the line, 2, 1, minus 3, plus lambda times the direction of the line, which is the same as n. So this is our n, remember, R dot n equals 6. So that's 3, 0, minus 4. Our next step is to find this point P here, where the line meets the plane. So we'll sub the line into the plane to find that out. So we've got 3 lots of 2 plus 3 lambda minus 4 lots of z, which is minus 3 minus 4 lambdas, and that all equals 6. So multiplying that out, we've got 6 plus 9 lambdas plus 12 plus 16 lambdas equals 6. And if you mess that one about, we'll end up with 25 landers equals minus 12. And that's right, is it? Yeah, minus 12. So then we just have with lander equals minus 12 over 25. Does that cancel down? I think it might. Put it in your calculator. Oh, no, it doesn't. No. Okay. Right, hence, we're trying to find where this actual point P, where the line hits the curve. We know that that's when lambda is that. So just put lambda is that into there. So we've got R equals 2 plus minus 12 over 25 times 3. And you end up getting nasty fractions. 14 over 25, I think. Check my maths, please. 1 and minus 27 over 25. Now we just have to find the distance between that point and the end point with a bit of Pythagoras help. So it doesn't matter if it's PM or MP. From MP, so I'll do P take M. So 14 over 25 minus M all squared plus 1 minus 1 all squared plus minus 27 over 25 minus 3, so ends up plus 3 squared, and that all comes to, I believe, 12 over 5, something I did earlier. Please check it and see if that makes sense. Here's some for you. Right, here's one for you to have a go at. So pause the video and have a go. It's the origin to that point, so it's the 0, 0, 0 to the point like the first one I did. Okay, probably unpause now, and here's the answer. Did you get it? 4 over 5. Put a perpendicular. Equation of the line. Hopefully you did. Here's another go. Have a go at this one. No longer the origin. Press pause. Okay, you've unpaused by now, and here's the answer. Oops, I think I'm covering it. Tell you the answer there. If you've cut it down and put it in your calculator, 14 root 3 over 3, or a decimal equivalent if you've got decimal equivalent. Check it. Okay, last bit of this lesson. Well, not last bit, is it? The second point on this lesson is actually finding points of reflection in a plane. So the reflection of M in the plane is M dash. So let's put that here. So if you've got this point here, M, you reflect it in the plane, you'll get this point here, M dash. So MM dash is perpendicular to the plane. It's the shortest distance. And the distance from M dash to the plane is the same distance as M to the plane. Pretty obvious. So we can write PM is equal to, so going from P to M is equal to going from M to P. That distance is the same as that distance. If we write these in vector form, we'd have M dash as a vector minus P equals, second one first, P minus M vector. And if you rearrange that to find M dash, because that's what we're after, we'll get, taking that over, 2P minus M. So you can calculate this point of reflection with this little formula. Because it's a vector. Or you can just use common sense. I'll do it in a minute. So from our example 2, the plane, that's a funny symbol for the plane. The plane was that, and we were given this point here. We found the perpendicular, this is in example 2 that I did a while ago, was that thing. Now find the reflection, so that's our P, if you want to label that on there, that's P, and that's your N if you like. Now find the point of reflection of M in the plane. Right, we could use this formula, and I will do in a second. Split this in half. It's just common sense. If M to P, if we've got like this goes, if we think of it as this is your M, so M is 2, 1, minus 3. To get to the plane, what's happened? The plane is 14 over 25, 1 and minus 27 over 25. So what we do to get to there, we do again to get to M dash. So there's your M, P, M dash. So you can just see what happened. What do you do to 2 to get 14 over 25? We've taken away 11 over 25, haven't we? So we need to take away another 11 over 25, and you'd be left with 3 over 25. What have we done to 1 to get to 1? Well, nothing. So do nothing again, 1. What have we done to minus 3 to get to minus 27 over 25? Well, you've added a bit, haven't you? You've added 1, and we've added 1 and a bit. In fact, you've added, gosh, yeah, 1 and 23 25ths. If you add 1 and 23 25ths, you'll end up with 21 over 25. And that's your M dash. Or you could just use this formula here if you want to remember formulas. M dash equals 2P. So times those by 2, you'll get 28 over 25, 2 and minus 54 over 25. And then if you take away M, which is 2, 1, minus 3, you'll end up with exactly the same point as we did using common sense. 3 over 25, 1, and 21 over 25. All done. Hope that made sense. So here's another one. You try on your whiteboard. Given that's the equation of your plane, find the equation of the line which is perpendicular to this plane which passes through that point. So that's going back to the first bit of what we've been doing in this lesson. So remember, your n for that one will be 3 minus 1, 1. And you need a line, equation of the line which goes through there and travels in that direction. Easy, maybe. Hence, then you've got to find the distance from M to lambda, not M to lambda, that's M to the plane. So that's just what we're doing in the first bit of the lesson again. And then, this part C, find the coordinates of the reflection of that point to the plane. So you can either use the common sense method or the formula. Off you go. Please pause. Okay, unpaused. And here are the answers. So there's the equation of the line, there's the distance, and the last bit, the new bit, if you use the formula, there you've got that. Hopefully you've got it. Right. There's an exercise to do, and there's a full exam question here that you might wish to try. Well, you might not, but you've still got to do it, so have a go. I'll read it for you first and give you some hints if you need it. Pause now if you don't want the hints, or if you want some hints, keep listening. So, we've got 2 lines. Yep. Given that line 1 and line 2 contained within the plane, so that means that if you want to draw a picture, let's draw a picture. There's your plane. Here's one line, here's another line. So that's quite R1, R2. have to, well, I'm not touching at this point, do they? R2, right. Part AI, find the Cartesian equation of the plane that is independent of A. Here comes the foxy bit. So normally, if you're trying to find the equation of the plane, you know n, the perpendicular to the plane business, is that cross that. But you can't do that cross that because it's got A in it and it's just got to find it independent of A. Do we need to find another direction on this plane? Well, we do know 2 points on this plane. We know this point here, which is your, if you call that A, oops, that's point A. We know this point B here, B. So you can actually find the direction of A to B. So if you find me the vector A to B, that's another direction on that plane. And then you can do that direction dot to the direction on R1, not dot, sorry, cross, my fault, cross direction on that one. And that will then give you your n, which is the perpendicular bit to the plane. And once you've got that, it's straightforward from stuff we've learnt in previous lessons. Have a go. Oh, and if you're still looking for hints for the next bit, find the value of A. Well, there's a few ways to do that. You can either say that this line here must lie in the plane you've just found there, so you can sub that line into the plane and you'll find A that way. But you'll also have to then just let mu be any number you want if you want to try it that way. Or maybe more sensible would to say, well, this lies on the plane because we're told so. So we know that that thing dot the n value that you'll have found by doing that, if the perpendicular, then you know that the dot product is 0, and then you'll be able to find A that way. I think that's a bit simpler. Then the last point, last part, shall I say, coordinate this is reflected in the plane to give A dash, gives you that. That's what we've just been doing, so I don't need to give you any hints there. You'll be able to do that. So please pause, and then you'll find the answers come up. So pause now, have a go, and see you in a minute, or maybe 6. Okay, unpaused, and here come the answers. So that's, as we said here, normally cross those two, but no point because it's got A in it. So you find that other direction, that, cross them, and it gives you 18, 36, 36. Well, you could divide 9, 18, 18, or even better, you could have done 1, 2, 2, couldn't you? Should really put there. Or 1, 2, 2. You can take any scale factor out. If you looked at 18, 36, 36, it really doesn't matter. And then equation of the plane, r dot n equals a dot n. Equation of the plane. Right, you're told that to find A now, so you know that line 2 lies on the plane, so you could have done it like that. Then let mu be any number. I chose 1 and found it that way. Or I said more sensible, you should know that because that direction lies on the plane and that's the normal to it, then dotting them gives you 0. If you dotted them, you end up with A is minus 4 again. Makes more sense. And then the last bit, find the perpendicular vector through A to the plane. There's the equation of the line for going from this point, if you like, P to A. And then the foot of perpendicular lies in the plane, so you have to see when does this line hit the plane, put that into our plane formula. Gives you land as minus 5 over 18. And then I've used common sense, but you could also have used that m dash equals 2p minus m if you preferred, and you'd have still got this answer, minus 2, 0, minus 20. Okay, that's the end of vectors. I'm sure you'll be sad to hear. The next topic we'll be doing is matrices, which is sort of similar. We'll try and make it a bit of fun, maybe, or maybe not. Anyway, have a go at those questions that are then set, and I hope they keep you entertained. Goodbye for now.